Well, hello there. Are you ready for your next lesson? I'm standing in for Dr. Blyle. I'm Rashina. I used to date a woman, and every time I would use this voice, she would get so freaked out she would literally shudder. So this is the voice I'm going to be using today. All day long. Are you ready? Okay. Seriously, is anybody still watching these things? Am I wasting my time? I've not heard from anybody in quite a long time. So I'm wondering if we're actually still doing this or if I'm just kind of pissing in the wind here. I don't know. Chapter 7 is an odd chapter. Truly odd chapter. We covered part of it. I don't think this is going to take long today because we covered part of it already last time. It picks up again with trigonometric functions, and then it goes into hyperbolic trigonometric functions, which are a whole new class of weird. Okay. Let's talk about, first of all, the unit rod diagram, which is where chapter 7 starts. The unit rod diagram is a circle with radius 1. That's where the term unit comes from. I know you're expecting me to make a penis joke, but I'm not going to. I'm above that. Well, if you have a unit rod, then you probably better buy a Harley. Make up for it. Anyway, if we drop a segment down, we have a right angle here. We have an angle alpha here. And notice that we have a unit length that we're going to call, I believe the book calls this A, or let's call this X here, and Y here. So we have some value of Y, which is the same as that. We have some value of X. And this is true as we take that unit rod all the way around. 180, 360 degrees. My wrist doesn't quite flex that way, so it doesn't quite get far enough. I should be a hand model. Okay, now the book goes through and derives certain values for sine and cosine using, if you recall, our Pythagorean theorem. We know that x squared at any angle, plus y squared equals h squared, the hypotenuse squared. But the hypotenuse is 1. Therefore, 1 squared is equal to 1. So in our unit rod diagram only, the unit rod diagram, and it's only because the radius equals 1, x squared plus y squared is equal to 1. And from this they derive certain values of sine, certain values of cosine, like I did last time. It's the same thing. If your value alpha (0 degrees or 0 radians, depending on what you want to use, that essentially means that this is sitting right on the x-axis. And if that's true, if you kind of think about taking this and moving it down to the x-axis, then r, or the hypotenuse, equals the same as x, y is equal to 0. Sine, recall, is opposite over hypotenuse. Well, if you take this angle to 0, the opposite, which is the value of y, goes to 0. Therefore, in this case, the sine of 0 is equal to 0. Because the opposite length has gone to 0. And 0 over the hypotenuse, 0 over 1 equals 0. Cosine, on the other hand, is the adjacent over the hypotenuse. Well, this is the adjacent. X is the adjacent value. And if you think about taking this down to 0, this is going to be the radius and the x value are going to be exactly the same. So the opposite over the hypotenuse, they're the same. They're both equal to 1. 1 divided by 1, and we get cosine 1. The other extreme, of course, is to take alpha to 90 degrees. And recall, that's pi over 2 radians. So if we take this and move it straight up, well, in this case, x equals 0. And if x, remember, x is the adjacent. If the adjacent is equal to 0, if that x shrinks down to 0, that means that we have 0 over 1. And that's 0. But the opposite, which is y, the opposite becomes equal to the radius. And we get 1 over 1. And that's going to be equal to 1. The book goes on to plot this the way that I did last week. So we're done. That's fine. There's one other angle that you should be aware of. Pi over 4, or 45 degrees, which is actually kind of close to how I drew it here. If alpha equals 45 degrees, or pi over 4 radians, pants are falling off. I just can't keep weight on. I'm probably dying. I'm looking forward to death, so that's not a bad thing. At 45 degrees, we have an unusual situation, because at 45 degrees, or pi over 4 radians, remember, here we have 0 radians, here we have pi over 2 radians, here we have pi radians, and so forth. This would be half of this distance, half of pi over 2. It's pi over 4. At pi over 4, when this is exactly halfway to the 90 degree, if you think about this, you'll realize that the value of x equals the value of y. Okay? So at 45 degrees, x equals y. And what they tell us is cosine of pi over 4 is equal to sine pi over 4 is equal to root 2 over 2. Is that correct? Well, I want you to think about this. The hypotenuse for our unit rod diagram, and the unit rod diagram alone, again, we're talking about where r equals 1, which means h equals 1. So again, we're talking unit rod diagram only. Do not confuse what I'm doing now with a generalization. We are only talking about one specific case where we have a hypotenuse equal to a radius equal to 1. Well, if you think about this, sine, which is opposite over hypotenuse, is opposite over 1, is opposite. And the opposite is our value of y. For the unit rod diagram only. Again, I cannot stress that enough. Same thing, we can play the same trick with cosine. It's adjacent over hypotenuse, which is adjacent over 1, which is the adjacent value. The adjacent value is the value of y. So cosine of alpha equals x. That is true all the way around the circle if, and only if, we have a unit rod diagram. Well, if sine of alpha equals equals y, and cosine of alpha equals x, that means sine squared of alpha is x squared. And cosine of alpha, actually I need to show you something here, is squared. Notice I moved that 2. There's a reason for this. If we write, say, tangent of some angle beta, whatever it might be, if we write this, it's confusing. Does this mean we square the beta? Or does this mean that we square the tangent? By convention, anytime we are squaring a trigonometric function, okay, I'll play with the nipples. Every time we're squaring a trigonometric function, we put the square by the function. So really, the proper way to write this is sine squared alpha. That means we're squaring the value of the sine of the angle. Same for cosine. Cosine squared angle means we are squaring the value of the cosine of the angle. Well, from this identity, again, for unit rod diagrams only, we know that this has to be equal to 1. So if cosine of our angle, which happens to be pi over 4, cosine of our angle is root 2 over 2. That's the value of sine. We're going to square that. Cosine is the same. If you square a fraction, you have to square both the numerator and the denominator. So this becomes the square root of 2 squared, which is 2, divided by 2 squared, which is 4. Same thing here. Square root of 2 squared is 2. Square of 2 is 4. And if you work this out, well, 2 over 4 is 1/2. 2 over 4 is 1/2. 1/2 plus 1/2 equals 1. So yes, that is true. That at 45 degrees, for a unit rod diagram, actually, you know what? Yeah, we'll do this first. So anyway, at 45 degrees, the value of sine and the value of cosine of that angle is both square root 2 over 2. By the way, way, the cosine values, the sine values are true whether you have a unit rod diagram or not. Because if you have something other than radius equals 1 here, you extend this out, you're going to expand the x and the y by the same value, and the ratios are going to remain the same. So the unit rod diagram is only useful for determining some common values, some common values of sine and cosine. And what have we discovered? 0 radians, pi over 4 radians, pi over 2 radians. You can extend this. It's not hard. The next one would be here, which would be 3 pi over 4 radians. And what's different here? Well, this is still a 45, well, you think about it, we've gone past this point. Now our x value is negative. We're in the negative realm for the x value, but y is still positive. So this value is not going to be root 2 over 2. This value is going to be negative root 2 over 2 for both sine and cosine. At 90 degrees, again, y has gone to 0. So our sine is going to be 0 at pi. Our cosine is going to be 1. This is not pi over 4. This is, well, I'm sorry. Confusing what I'm doing here. This is 3 pi. This is going to be 2 pi. Oh, Lord, I can't even think anymore. I'm so tired. All right. So we have 2 pi here. We have pi here. 2 pi, this is going to be 3 pi over, no. Three pi over 2, yeah. So here we're at 3 pi over 2. Of course, here we're at 2 pi. This direction, 0 pi if we're going this direction. This then would be 5 pi over 4. This would be 7 pi over 4. Okay, anyway, the point being, you can figure out the values of sine and cosine by continuing around and just remembering we're at negative x here, we're at negative y here, which means that if we're at 5 pi over 4, we have negative x divided by negative y, which means we're back to positive root 2 over 2. This is a cluttered mess, and I apologize for that. The book kind of has a little bit more, but take a look at it. I think that you'll see that it kind of makes sense. You can verify all this with your calculator. I'm not going to go through every major point. I've shown you how to do it. Remember, at these values, x equals y, and the only difference is one of them might be negative. If one is negative, you get negative root 2 over 2. If both are negative, you get positive root 2 over 2. Here, figure it out. It's x is negative, so we're not going to get, see, opposite is sine. So sine is not going to be 1 because you don't have y over, I'm sorry, because the x value here is negative 1. Negative 1 divided by 1 is negative 1, so sine is going to be negative here, and so forth. Cosine is going to be negative here. The book goes on to talk about hyperbolic functions. I'm going to be honest with you. I've worked with hyperbolic functions. When we talk about high-level theoretical physics. You get into hyperbolic functions. Before that, you don't. Function. The simplest, y is equal to some value over x, or 1 over x is actually the easiest. Y is equal to 1 over x. As x goes off to infinity, we're going to become asymptotic to the x-axis. Remember what asymptotic means. Asymptotic means we get closer and closer and closer to 0. We never quite reach it. So we become asymptotic to x to the x-axis for very large values of x, because 1 over infinity approaches 0. It's easy to figure out. I mean, you know this. 1/2 is greater than 1/4, is greater than 1/8, is greater than 1/10, is greater than 100th, is greater than 1/100000th, so forth. It gets closer and closer to 0. As x begins to approach infinity, as x begins to approach 0, y begins to approach infinity. So we become asymptotic to y as x becomes close to 0. Now if you want, you can plot out, and of course this also makes sense. 1 over 0.1 is 10, 1 over 0.01 is 100, 1 over 0.001 is 1,000. So we get closer and closer and closer to that x-axis. This value of y goes up and up and up and up and up. Never reaches. It's asymptotic. Never quite gets there. But closer and closer. If you want, you can do a couple of other ones. You can do x equals 1, 1 over 1 equals 1, so you can plot that. Be around here somewhere, and you end up with a graph. It begins to look more symmetric than I'm drawing it, something like this. But that's not all. X doesn't only have positive values, does it? X also has negative values. Well, 1 over -1, as x goes to negative infinity, this is still going to go to 0. But it's always going to be negative because x is always negative. So again, we're going to become asymptotic to x, but on the negative side of y. Okay? 1 over -2, 1 over -3, 1 over -10. It's all negative, but it's getting closer and closer to 0. Same thing happens as x approaches 0 from, and by the way, this is something that you're going to learn in calculus, is directionality of these math functions. X approaches positive 0 from the right. So as we approach x from positive values from the right, remember your number line, right is always more positive than left. So as you approach 0 from the right, you're going to approach positive infinity. As you approach 0 from the left, that means always negative values for x. Y is always going to be negative. You're still going to approach infinity, but now you're going to approach negative infinity. And you're going to get a graph. Again, 1 over -1 is -1, so you can plot that. And you get this. And this is a hyperbola. A hyperbola has a couple of features, too. And your book doesn't talk about this. This is for your own edification. I want you to understand, if we're going to talk about hyperbolic functions, you should know what hyperbola means. A hyperbola has a couple of features. First of all, it is symmetric. And the way I drew this is so bad, I'm going to try and redraw it, because it really is symmetric and not the way that I drew it. So it's going to look something, that's a little better. Still not quite as symmetric as I would like. These two images are mirror images of each other. There's kind of a mirror plane goes through at an angle right in between. So a hyperbola always has two parts to it. They are always mirror images of each other. Each half becomes hyperbolic to an axis, to two sets of axes that are at right angles to each other. All right? In other words, we have two sets of axes here. We have the x-axis, we have the right axis. The y-axis. The x and the y-axis are at right angles to each other. The hyperbola becomes asymptotic to each of these axes on both sides. They never reach that axis, but they get closer and closer and closer to it. Okay? That's a hyperbola. The generalized form of the hyperbolic function is this. This function, depending on what A and B is, you can kind of skew it a little bit. But here, the two axes are actually at 45 degrees and 135. And you get a function that looks like this. Again, two sides that are mirror images of one another. They both become asymptotic to an angle, to an axis and to two axes. They both become asymptotic to not one but two axes. And the two axes it becomes asymptotic to are at right angles. You're going to hear about conic functions. Well, you know what? Let's not talk about that. You don't need that. So what are hyperbolic sine and hyperbolic cosine functions? The book makes a couple of statements that to me make absolutely no sense whatsoever. I think that the author may have been drunk while writing this part. The book reads, for example, on page 88, looks like, f of x equals sine of x has no inverse in its natural domain because the function can be used to assign to every y a number of values of x. Okay. I understand what that means. I don't see why it doesn't mean you can't have an inverse. At every y, there are a number of values of x. Okay, that's true. I lost my black pen. But I bought one or two just for this course. You know why? Because I am a dumbass. All right. So we talked about sine. This looks like this. What the book means is for every value of y, you can assign many values of x that will give you that same value. In fact, that x, that circle, if you take that radius and you just keep going around and around and around, how many times can you do that? Pretty much forever. which means that you can assign pretty much an infinite number of x values to give you the same value of y. And so on. So what? The definition of a function is that for every value of x, there is one and only one value of y. Nothing in the definition of a function says you can't go the opposite direction. There's nothing that says that you cannot, for a true function, have more than one value of x that gives you the same value of y. This is a valid and legitimate function because any value of x only has one value of y. Just because any value of y has more than one value of x, it doesn't mean anything. It doesn't mean it's not a function. You want to see the inverse of this? There's your inverse function in blue. So why the book says you cannot have an inverse function, that to me makes no sense. I've never heard that anywhere else. It is, to me, it blows my mind. And then the book goes and tries to do something kind of weird with that, and they do it at an angle instead of what they tried to do is they said, all right, well let's change this function. So instead of going like this, it's going like this, and now for every value of x, let's do this in green. And there are mathematical ways to sort of transpose this. You can transpose any function, so all of a sudden you just change where the axis is. You have to be careful. You can't change it so that the axis is straight up and down because you don't have a true function then. But if you have an axis like this and a sine function, if you do this right for every value of y, and obviously I didn't, you should have only one value of x. And then they say, oh, that way you can do an inverse. Well, no, come on. It's all crap. You can do an inverse for sine and cosine in its normal area. So that makes no sense to me. But that's what they're trying to do. At least I understand what they're trying to do, which I guess is at least a step in the right direction. So let's get back to hyperbolic functions. You designate a hyperbolic function by using the value h rather than just, so instead of sine, it becomes sine h of some given angle. This is defined in exponential terms. This is equal to e to the value of alpha minus e to the negative value of alpha. Is that right? Yes. Divided by 2. Cosine h, or hyperbolic cosine, plus this is the definition of sine h and cosine h. I believe, and you know, it's funny because in the book, by the way, the book goes through how to plot this. And the way the book does it, it's pretty simple. You come up with two tables. First table, you plot e to the alpha. Well, e to the alpha is 1. I'm sorry, e to the 0 is 1. E to the 1 is e, and so on. And you plot several values of alpha and what the number is. In the second table, you do e to the negative alpha. You do the same thing. You can do this on your calculator. Just punch it in, come up with the numbers. It's easy to do. And it says to plot sine of h, come up with the third table where you subtract the 2. To plot cosine of h, come up with the third table where you add the 2. Then divide by 2 in a fourth table. Oh my God, are you kidding me? I don't see the point of that. Here's where, in high energy physics, in very high level theoretical physics, this comes into play. And I'm not even going to go into why or how it happens. I'm just going to tell you flat out. In quantum mechanics, when we are trying to describe the behavior of electrons, there are certain rules that we have to follow. As it turns out, these exponential values follow those rules. In calculus, we're talking mathematical rules, basically. The mathematical rules do correspond to physical reality. But these functions, exponentials, follow those laws, follow those mathematical equations. But the problem becomes, do we take the positive or the negative value? Sine h and cosine of h combine those two. That's why we use hyperbolic functions in high energy physics, because it combines both possibilities and therefore both legitimate solutions to the problems that we're trying to solve. Stick with chemistry and physics and high level math, and you're going to use hyperbolic sine and cosine. If you decide you do not want to go into the high energy physics, oh, how sad. Most calculators, but obviously not this one, most calculators will have a set of regular sine and cosine functions. Can you see that? I can't. I have a tiny little LCD screen. I can't tell if you can see it or not. But most higher end calculators will have a regular sign of sine, cosine, tangent, and then very near there's going to be a second set that is sine h, cosine h, tangent h. And what you're going to find is, until you get into high level physics, you're not going to use this, except in math problems and books like this. And that's about it. There is one, and something else to remember. Your book gives several mathematical identities. There it is. That are important to know. Mathematicians might be able to explain hyperbolic functions better than I do. For me, there's no practical value outside of physics. But the book gives several identities in trigonometry that you should at least be comfortable with. Here's one of the more important ones. Let's start with sine. This is always true. Sine squared of x plus cosine squared of x. Oh, I should have done it the other way. You know what? I'm going to rewrite this. Because, remember, addition is commutative. It doesn't matter the order. So we can flip these two. So let's flip them. I'll show you why in a moment. So the cosine squared of x plus the sine squared of x. And the book has many more identities than this. I'm not going to go through them because you can read. That equals 1. Well, here's a very important hyperbolic trigonometric function that's important. There you go. It's an analogous equation, and I think this is probably why the term cosine h and sine h are used, because this identity is true. The only difference, and they look very similar,
The only difference is if we're talking hyperbolic, we're subtracting sine h squared from cosine h squared. If we're talking simple trigonometry, then we add cosine. Are actually very important identities for trigonometry and hyperbolic trigonometry. I kind of warned you this was going to be a short one, and I think that's it. I'm pretty much done. So, with that, I hope that you all are having a great weekend. We are in the middle of Sturgis Rally Week, which means that Rapid City and the Black Hills area is inundated with motorcyclists. It's a frightening thing. It's kind of a small area, and the roads are really not, they get plugged up pretty quickly. They're not designed for this kind of influx. There needs to be more infrastructure in the region. We will at least double the population of South Dakota for the following week. Probably even triple it. So, I have a busy week ahead of me. I hope that your week ahead of you is wonderful and joyous. And let me know if we need to keep doing this or if we're done, because I'd kind of like to know. I've not been getting any feedback, and that kind of bothers me a little bit. So let me know if you're watching these. Let me know if you're getting anything out of them. Are you watching them just to see me make a fool of myself? Because that's the wrong reason. Are you actually learning? Are you actually doing the homework? Are you actually reading is the question. And if you're not, that's okay. This is your course. But let me know. All right. Thank you very much. Have a good one.